All right, so for any students or anyone who has been studying integral calculus with me, so I now believe that as you have arrived at this video lesson, you must be enjoying your days and working through the fundamental theorem of calculus, the second part. That fabulous, sweet, beautiful tool that allowed you, that unlocked that secret of how you find the final answer of a total accumulation, but without really doing the accumulation. Okay, so that was the whole idea of the fundamental theorem of calculus, the second part. But now, as we have worked through enough with problems and as you have built enough confidence in your problems, some of you might start thinking a little further. Okay, so now what is that further thinking that I would like to mention about? So let me now bring the fundamental theorem of calculus, part 1, the fundamental theorem of calculus, the second part, back on the screen right there, so that we can have a good review of what that result was, and then I'm gonna be able to dive in a little more detail to start pushing you into understanding why there has to be a what's so-called a fundamental theorem of calculus, but the first part, or part 1 right there. Okay, and so now let me bring it on screen right here, the fundamental theorem of calculus, the second part. All right, so on our screen here, this is what we primarily study. This is what we study and used prior to this point right here. Let f of x be a continuous function on an interval from anywhere from a to b. So as long as we have our function f of x satisfy those little requirements, being a continuous function in an interval from a to b, then the accumulation. So now again, I highly recommend any of my students to see an integral, a definite integral, as accumulation. So a definite integral or accumulation from a to b can be found as a final answer, can be found by simply capital F of b minus capital F of a. Okay, and that's the highlighted part. So I had an explanation of what this is back in my formal video lecture when I was explaining about the fundamental theorem of calculus, the second part. But here, more importantly, the function, the capital F here is related with the lowercase f, because recall again that in this theorem, what we're doing here is we're accumulating on the lowercase f of x function. So magically, what is this capital F function right here? So the little explanation is here. Capital F of x is that function where it satisfies capital F prime of x equals f of x. Okay, and so now, logically speaking, let me now unhighlight this area, these two parts right here. Logically speaking, well, this is the fundamental theorem of calculus, the second part. But so now back in what I was in the middle of saying, logically speaking, this theorem mainly allowed you, and it still is, it's still the one, it mainly allows you to evaluate once you have found the antiderivative of your main function f of x. And how do we know it's the antiderivative? Because that relationship is being pointed out right here. Okay, so once we have found, so when I say once we have found, that means the step of evaluating, subtracting f of b, subtracting capital F of a from capital F of b, that subtraction step is one step, but must be done after we have obtained this capital F prime right there, which is now namely the antiderivative of our main function, lowercase f of x, indicated in the definite integral problem. So in the end, my point now is that this fundamental theorem of calculus, the second part that we have been using up to this point, really, that result we've been using has two logical parts in it. One part that we've been mostly focusing to is the part where we substitute. So the part that this theorem itself mostly focus is the part where we can substitute the upper limit of our integral into the antiderivative, and also substitute the low limits of our integral into the antiderivative, then subtract out. So that is the main logical part of the second fundamental theorem of calculus. Okay, But now if we're looking at that one more time and start pushing our curiosity a little further, then in that way, how do we know? How do we know? Let me now unhighlight a couple of things right here. Okay? So how do we know how do we know that doing this work first requires us to find the capital F, find the antiderivative of lowercase f? Because we know it has to be the antiderivative according to this result right here. So once again, ultimately, as a question I'm raising here, how do we know that it has to be first to find the antiderivative of our main function? Okay, because now as I have just unlocked, this theorem you are seeing on screen is only guaranteed that once you have already had the antiderivative, then you can take that antiderivative, evaluate it at b, and subtract that same antiderivative evaluated at a, and then that answer is going to be your final answer for this total accumulation. But now again, I'm raising that question, how do we know it has to be, how do we bring that connection between the antiderivative and the accumulation work? That's the part that's now I have to introduce for you. Historically and logically, there has to be another part of the theorem that's now we so-called the fundamental theorem of calculus, the first part that allows you to point out that connection, that relationship, that anytime we are doing accumulation work, then generally speaking, what we need first is to find the antiderivative, the part being highlighted right here on my lecture note here. Okay, and so in that way, now allow me to write down the theorem here on the board. So this theorem, yes, it's called the fundamental theorem of calculus. The fundamental theorem, and again we can refer to this as the FTC. Okay, the theorem, the fundamental theorem of calculus. But now I have to highlight it. This is the first part. Okay, and so a lot of time you might hear people referring to this as the FTC part 1, or just the FTC 1 right there. Okay, so yes, in the way how it's stated, then historically speaking and logically speaking, this part must come out first to set a foundation for your second part of the theorem to come in. But now you can start seeing it in my style of teaching. So that's why I was now earlier in the beginning of this lecture I was communicating to the students who have been following with my style of teaching about the fundamental theorem of calculus. I see the usefulness, the immediate usefulness of the fundamental theorem of calculus, the second part. So I tend to teach that first, so that student can, immediately after students get out from the deadly accumulation work, which is done through the Riemann sum and taking limits to infinity, then student can start enjoying immediately that result stated in the fundamental theorem of calculus, the second part. And now once any of you, the students in integral calculus have had enough experience with that, and start pushing your mind and start gaining some more majority and start pushing your mind into some more curiosity, okay, and, in terms of how these theorems got developed. And now you are ready to start understanding that historical part and also the logical part, where it set that foundation for your fundamental theorem of calculus, the second part. Okay, so here we are at that fundamental theorem of calculus, the first part right here. Okay, so I highly recommend that if you don't know what I'm talking about in terms of the fundamental theorem of calculus, the second part, view my earlier video lecture where I was explaining in details what the fundamental theorem of calculus, the second part, does for you. Okay, and how useful that is. And here we're gonna explain the historical part that came before the fundamental theorem of calculus, the second part that you have been doing, that you've been working with. Okay, and so now here it is about the fundamental. This is the wording right here, and allow me, I would like to stick with the traditional style of teaching math where I write the theorem itself, but indeed you can always find the precise wording of this theorem, of any of these theorems here in any standard calculus textbooks. But allow me to write it on screen So, and I highly recommend that you take note as well, so that you can start getting a good catch of it. Okay, but do forgive me in case I don't write down in case my wording is not as precise as how it's given in any of your standard calculus textbooks. Okay, so now I'm going to start out by saying, I'm going to say let f of x, or assuming f of x, lowercase f of x, okay, be a continuous. Okay, so all integral work is based on a continuous function. So let f of x be a continuous function. Okay, on that interval from a to b. So in that closed brackets interval from a to b, we have f of x being a continuous function. And so in that way, this is the part that's quite fascinating, and I will have to give a lot of explanation as once I finish with this writing down, with this writing right here. So I'm writing it down and I'm breaking it down at the same time. So now we have another function outside of this f of x right here, outside of this lowercase f of x. Okay, I'm going to define a function. There's another function. So just treat the function that I'm about to write here as a separate function, a function completely separate from f of x here, the function g of x. Okay, the function g of x. That is defined by the function g of x, defined by the following. G of x is defined as an integral, a definite integral from some value a, from a, the beginning of your integral window right here, to some x value, okay, some x value, not to b, from a to some x value, but as accumulation on that function f of t dt. Okay, so now I need to pause a little bit and clarify it. I had at the end of that video lesson where I mentioned, where I explained in details about the fundamental theorem of calculus, the second part, and I also explained that now when you are looking at an integral problem, a definite integral problem, or even an indefinite integral problem, then the variable's name that you are using here is not important. What matters is as long as you are doing your d expression is consistent with your variable name that you are using. That's what's good. So mainly you have a function, because in case anyone is shocked, how come I started out writing f of x and here I'm using f of t in my integral? So that's what I meant earlier by, the name of the function shouldn't, the name of the variable should not matter. Okay, what we do here is we're accumulating stripes at any instant. Okay, at any instant, the stripes of a function multiply with the thickness of each stripes, and then we're accumulating from a to x right here. Okay, but now so that's one clarification, but now I have to explain what x is. But x here has to be a value anywhere between. So you have a window, an interval from a to b, and I keep using that term window because I want to bring up that geometric interpretation of that. You got a graph and you restrict your graph within this window from a to b. And so x is a value chosen, but anywhere, an arbitrary value chosen anywhere from a to b. Okay, and I will also put that on the actual nice graph with decimals here. So this is the way how we define our g of x function. G of x comes out, okay, g of x is defined as a function that comes after a accumulation. At this point, you gotta start letting that idea being fluent in your understanding. A definite integral is accumulation. Okay, what are we accumulating? We are accumulating stripes, the striped areas that comes out from stripes multiplied with thickness dt on your function f of x. We accumulating all of those stripes from a to x. Okay, a is that fixed point, and x is just some point inside of your interval from a to b. Okay. This is only halfway of the theorem, but now let me really explain, because you have to understand what this function g is in order to really understand the core, the good usefulness of your fundamental theorem of calculus, the first part that you're about to learn here. And so now allow me to swing by the computer and let's look at the graphing. Let's look at the graph that I prepared with decimals here. Okay, so this is our function f of x, some function f of x. Okay, and we don't have to worry about the scaling or how big is unit 1 or unit 2 or whatsoever. I completely hid away all of the numerical labels right here. Okay, so let's say the interval from a to b is some interval. So a is here, b is here. One weakness of decimals here is that I'm not able to label I'm not able to put the label directly here. Those kind of alphabetic labels. I'm not able to put those here. But so this is a, okay, on the x-axis, or now you can call this the t-axis, right? A is here, and then b is here. So that's the end of our interval from a to b. Okay. And now here's the idea. Think about an x value. So that's why I'm dragging my handle here. So right at the foot of our handle right here, right at the foot of this stripe. See, anywhere I'm dragging my window, anywhere I'm dragging my handle here. This on the x-axis is an x value. That's what I meant by it's an x value that is anywhere from a to b. Okay, so now think about as a consequence. Think about the consequence of having x, but x is arbitrary. X is arbitrarily chosen. So in that way, see how it happened on the graph when we were on the computer screen right there. I was able to move it back and forth like that. And so the further we move x towards b right there. See? So right now in my picture, x is still close to a, but the further we move x to b right here, then this is what happened. Now we notice the accumulation, the integral, the definite integral, is that accumulation which created this blue area for us here graphically. Okay, so now as we move this x here, keep letting this x coming closer and closer to b right here. Of course, our shaded area here will keep changing. Okay, and I am not saying that it has to get bigger or it has to be smaller. An integral is not necessarily an area. I've been emphasizing that earlier. An integral is just basically accumulation. And so again, back on our stripes, you see when we are going from a to x right here, then we already had a lot of stripes, and that's how it created this area in blue. Okay, so now, ladies and gentlemen, what is g of x? X is any arbitrary position of this handle over here. So g of x is represented graphically by this blue area. Okay, and that's why you can see that the value of our g function, depending on where we put, see, if I put my x here, our function g has an output has a different output because the area here is different than the area accumulated here. Or you can think of that as the accumulation. The amount of accumulation when x is here is different with the blue amount of accumulation when x reaches to here. Okay, and so now allow me to be on this board right here, and I was doing that demonstration with the blue color on my graph. So now I'm gonna say that yes, the blue one the blue function is the g of x. That's the blue function. Okay, and that blue is the area, and so we define that blue area. Now we enforce that idea. That blue area, that blue shaded accumulation, is the area that's accumulating from a to x right here. But the stripes comes out from our function f of x. The height of the stripes, of any stripes, comes out from our f of x function. And that's why using t here in respect to dt, that is completely fine. But now, once again, mainly I would like to emphasize, and that's why I'm writing that the g is in blue, because according to that demonstration in the picture right there, g is that blue area accumulated from a to x. And so now anywhere that we put x, according to the way how the picture was, and according to the way how we define our function g right here, then as we're moving that x handle, if you keep thinking back of that picture I put on the graph right there, then if we're moving that x handle closer to b right here, then the g function, the value of your function g become the total accumulation amount, becomes the total accumulation amount that happens anywhere from A to B on that function. Okay, that's what the function g of x is. Okay, so now once you've had that idea nailed down, now I am going to complete the actual statements of our fundamental theorem of calculus. So the function g of x, now once you have understood clearly what that means by we defining, so g of x is that function we purposely define. But once we define that function, here's what's shocking right here. Here's the shocking result. Okay, the function g of x defined by that formula. So that function must be a continuous function. That's one thing for clear. Okay, must be a continuous function. Okay, on the interval from a to b, of course. Okay, and differentiable. Okay, so this is one term that we bring back from differential calculus. I'll name a lot of colleges refer to that as calculus 1. It's one term we have to bring back from calculus 1 because the term differentiable means our current function now that we're focusing on. If we define it that way, then we can always take the derivative. That's what differentiable means again. That's what differentiable means. Okay, and of course I also have video lessons on on differential calculus or calculus 1. So find my videos for calculus 1 where I taught about what it means by being differentiable. Okay, so the function now in calculus 2, in integral calculus, now we learn that this function, in the way how we define it as currently, it will be, the function g will be a continuous function. And further it will be differentiable, meaning you can take a derivative anywhere on the open interval from a to b. Okay, and now I'm running short of my board space right here, so I'm gonna have to continue that on my other board. Or actually, let me attempt to write it a little smaller so that I can fit it all in here. Otherwise, it's gonna make it more confusing. Okay, so that function g of x is continuous on that interval. Okay, and differentiable on the open interval from a to b. And now more importantly, the derivative. Now, so saying that it's differentiable means we can find that derivative. So now the main part of this fundamental theorem of calculus, the first part here is guaranteeing now that when you take the derivative of this g of x function, you take the derivative of this g of x function anywhere, at least anywhere inside of this interval, then you will have the following. It will come out shockingly just the function f of x itself. That's the important part there. So g prime of x, the derivative, okay, the derivative of the function g. And keep in mind again, g is defined as a accumulating function. And up to this point, now I can officially start saying out loud the function defined like this is accumulating function, a function that came out from accumulating stripes. We have a lot of ways to come up with accumulation. I mean, we have a lot of ways to define a function. So now, as you have arrived to a calculus 2 course, a course in integral calculus, outside from defining a function being g of x is an x squared function, g of x is a 5x function, or defining a g of x as through a table. Now we can also define a function g of x through a accumulation. Okay, let your mathematical majority grow. Okay, and so now, once again, the function defined as accumulation like this, we call that function as a g of x. Now the real result here, that the fundamental theorem of calculus, the first part now is stating that taking the derivative of that accumulating function will shockingly give you that beginning function f of x. Okay, and so now long story short, so now everything we have done, there is simply one important statement. The accumulation blue function g that I made that graphical illustration on the graph, and now I know that g prime, see, that's why I'm writing it in blue, g prime of x will shockingly come out equal exactly f of x. That's what it is. Okay, but be careful with the variable a little bit. You see, x here is the variable inside a from to be a little bit, so g is a function of x. The main variable for our function f in the beginning could be whatever. So in the accumulation that it happened, we can use whatever name for our function f. But now when it comes to the final step, taking the derivative of g as a function of x right here, then our final derivative has to also be in terms of x. So that's how I see it. So this x here has to be the same variable with our g prime right there. But that's the result guaranteed by the fundamental theorem of calculus. Okay? All right. So much explanation. What's the usefulness of the fundamental theorem of calculus? The first part. This theorem now is the part where it guarantees, allow me to get back on that fundamental theorem of calculus, the second part that we have learned previously on the computer screen right here. So on my computer screen, the fundamental theorem of calculus, the second part is here. I am going to clear out a couple highlights. Okay, but I was saying earlier, this fundamental theorem of calculus, the second part, is mostly focused on once we have found capital F, we can just simply evaluate capital F at B and also evaluate capital F at A and subtract out the two. That's the main part that this fundamental theorem of calculus, the second part, focused on. But now back to that question of how I addressed that earlier. How do we know to find the capital F prime? I mean, how do we know to find capital F of x to be the antiderivative? Okay, then how do we know? We know that because we have the second. We know that because now we have the first, the fundamental theorem of calculus, the first part. So here is my worded one right here, the one that my typed version of the fundamental theorem of calculus, the part one. So anytime that we have a accumulating function, okay, then and that accumulating function is defined over an interval from a to b, then the derivative of that accumulating function has to be the function itself, f of x. Okay, the derivative of the accumulating function is equal to the function f of x in the beginning. So that means this is the result that guarantees for us that, hey, when you were doing part 2 right here, then all you have to do is find the antiderivative. Because now if you're looking a little more closely in this part 1 of the fundamental theorem of calculus, the fundamental theorem of calculus, the first part, and this relationship is telling me that our function defined here, our function g of x defined here, is nothing but just the antiderivative. That g defined. So another point to see here is that, so now from now on, this theorem is proven that any function that came out as accumulation, generally as accumulation on any other function, from inside an interval from a to a variable x value, then that function there will automatically be the antiderivative, because the relationship is pointed out right here. Taking the derivative of g equals f in the beginning. So that means the antiderivative of f is g. So now it guarantees further that g of x, the accumulating function, the function that came out as accumulation, will always be, or will generally be, an antiderivative of your beginning function. That's the usefulness. And so now we know that anytime we're using the fundamental theorem of calculus, the second part, to do the calculation. And now we are more sure that this has already been proven. It's proven in the first part of our fundamental theorem of calculus. Okay. So now after some explanation that I hope detailed enough. Okay. Let's bring up some examples where it can point out a couple of directions. Can point out a couple of the applications of the fundamental theorem of calculus, the first part. Now, when I'm bringing up these two, I've spent most of our time so far, I've spent a good amount of time so far to explain how the fundamental theorem of calculus, the first part, set a foundation for the second part to kick in. Okay? But now think about it. Historically speaking, part 1 came out first. Part 1 came out first. Then, according to result in part 1, Isaac Newton, it's Isaac Newton again. It was all Isaac Newton that came up with this. I should have also acknowledged that. This came out by Isaac Newton. Okay, that famous physicist of all time. So historically, again, back in what I'm saying, historically, fundamental theorem of calculus, part 1, the first part came out first. It set a foundation for the second part, which is what we've been doing so far, to come out. But then think about it. Of course, in terms of the amount of time, then there's always a little time that it takes between when the first part came out and when the second part came out. So if you roll yourself back and pretend that you were among those people back at the time when Isaac Newton came out with the first part. So think about once we had the first part, but before we had the second part, in that time frame, right after Isaac Newton came up with the fundamental theorem of calculus, the first part, but before he came out with the second part, what can be useful about this? Okay, what can be useful about this fundamental theorem of calculus other than just to set a foundation for part 2 coming later? Is there any other application? Okay, and that's what I would like to point out as example. So as I'm getting into any of these examples, it's starting to get a little abstract, but you have to keep pretending yourself that you are among those the people at that time where Isaac Newton only came out with the first part. And before Isaac Newton came out with the second part. Okay? And so now in that way, allow me to swing over to the second board right here. And I'm going to bring up a quick little problem right here. It's not even a formal example yet, okay? Let's do the following. How about I'm given a function, how about g of x, defined as accumulation. See, again, one big key to be successful in this problem is think of an integral. Anytime you see this sign, anytime this sign is brought to your attention, start having in your imagination, it's accumulation, accumulating stripes. Okay? And so now g of x is defined as accumulation. That's what it's given right here. Given that g of x is a function that came out as accumulating, let's say as accumulation from 0 to x. Okay, accumulation from 0 to x on a function like this. How about t to the 4th dt? Okay, and we have and now as part of this problem, as the instruction of this problem, let's find g prime. Okay, let's find g prime. All right. So the wording, the instruction of the problem seems clear enough. And for some people with good majority in math, they can start seeing that, hey, in this way, right, in the way how it is, yes, we have a function and we know the way how our function g is defined. We know how g is defined. Okay, it's defined as accumulation on this known function t to the 4th. On this known function, we're accumulating from 0 to x, okay, to get g. And so now we find g prime. So over my years teaching, my students commonly fell into the following mistakes right here, which can easily become a trap. Okay, so I'm going to have to point that out first, so that to prevent any of my students who who's watching this video lesson to, from falling into it. Okay, so I want to prevent anyone watching this video from falling into the following mistakes right here, and then following the following trap right here. So back in my earlier days right here, my students used to give me a defense as following. We can just we can just do this, t to the 5th times 1/5, take the antiderivative of our known function right here, and then and then do the evaluation from 0 to x. Okay, and then we're going to substitute x just because you knew the fundamental theorem of calculus part 2, the second part. So the second part say you can take the upper limit into your antiderivative, take the lower limit into your antiderivative. So your upper limit here is a 1/5 times x to the 5th. So that becomes a 1/5 times x to the 5th. Minus, now substituting 0 into that antiderivative, you're getting a 0. So really your final accumulating function here is 1/5 x to the 5th. And you believe that you have found g of x. You believe that that's your g of x. Okay, and then from that point, sweet, we have found g of x. So now finding g prime according to what the question is asking is easy. That's just calculus 1, the differential calculus stuff. We take the derivative of the 1/5 times x to the 5th. And that gives me x to the 4th. People believe, my past students, when classes were face-to-face, believe they have found the answer to this question by going, I'm talking about by going in that approach, by going in that route right here. Okay? But now I have to say it out loud for anyone. This is a trap right here. This is a wrong path. Okay, this is a wrong path, and anyone following this path, you are completely missing the point. You're completely missing the point. Okay, so why am I saying that? The reason here is that, remember, I talked about now any of these problems when I'm bringing it up. I'm talking about you gotta pretend, because how do you know to put this in? I'm talking about you got to pretend. I'm saying that you got to pretend that you only know g came out as accumulating function, but you have not seen. I'm pretending that. What if you have not seen the fundamental theorem of calculus, the second part? Because see, the essential work being used here is the fundamental theorem of calculus, the second part, the FTC part 2. But as I already made it clear, I already stated it clear. We're working on this problem pretending that we were right at that time in the history where Isaac Newton didn't come out with the fundamental theorem of calculus, the second part, yet. So without knowing the fundamental theorem of calculus, the second part, we are not able to do this. No one approved that for us. That's how math happens. We can only use a method that are proven. And proven means, that someone has to bring it to life, to bring evidence that it will always work. Okay, so if you're in that historical time mark there where Isaac Newton did not come out with the fundamental theorem of calculus, the second part, yet, then we couldn't go this route. But the problem was asking us to find the derivative here. And our function g, again, is, as a reminder, is a function that comes out as a accumulation on this known function. So that's only one way how I explain. That's only one way how I explain that you can't go this route. Okay, you can't go this route. Find the antiderivative and subtract, and then use the upper limits to evaluate in. Use the lower limits of the integral to evaluate in, and subtract out the two. This is cheating. Because we're using something that, if we were those people at the time of Isaac Newton and before he was coming out with the second part of the theorem, then we were cheating. We using to the people at that time, that's Mars. That's math from Mars. Okay, so we can't do that. And furthermore, here's another. Even if, I challenge you, even if we are doing a problem like this, after the fundamental theorem of calculus, the second part was released, it's still not the intention of this problem, because what if I put up a problem as following: g of x is a function that came out as accumulation of the function e to the t squared right here. Okay, then now I'm saying even if that you already had the second part of the fundamental theorem of calculus, how are we going to find the antiderivative of this? Well, what is the antiderivative? What is the antiderivative? Okay, what is the antiderivative of e to the t squared? Is it simple to find this thing? Okay. Is it simple to find this antiderivative of e to the t squared? And I'm talking about even if you have already seen, even if you're among the generation of those people who came after Isaac Newton has released the fundamental theorem of calculus, part 2 right here. Is this, for this problem, is it that simple? So finding the antiderivative is not always a simple thing as well. Okay? And so now, that's the point I'm trying to say now, is that we don't go that way of finding the antiderivative, because we know that this has to be the antiderivative, but I am not. The problem here is intending that we are not attempting to look for the antiderivative. So let's get back to that problem. Okay? But, so how about, I hope my wording will be clear a little bit, but without really getting the antiderivative. And without really getting, I mean we don't have to know what exactly the antiderivative of this is. Some antiderivative is easy, some antiderivative is not. Okay, but it's not the point. We can bypass getting the antiderivative. We only know that this is the antiderivative, but we don't have to know what that is. I don't have to know what g is. Okay, or how about another way of saying without knowing what g of x is. I mean, we only know g of x is accumulating function. Or now we know from the fundamental theorem of calculus, the first part, that this has to be the antiderivative. But we don't have to know, we really don't have to tear it down, and is it going to be an x to the 5th or an x to the 10th? That's the part we don't have to know, without knowing what g of x really is. Okay? Really is. We don't need to worry about that. We can bypass that. Okay? And so now, ladies and gentlemen, now with our understanding of the fundamental theorem of calculus, the first part, the answer is very simple. So I'm now going to make a statement right here. According to the fundamental theorem of calculus, the first part, FTC1, the first part, then g prime of x, I don't need to go shopping around find the antiderivative. This is the antiderivative. We just don't have to find a definite formula for that. We just don't have to find a definite function for that. But I know immediately that the derivative here has to be f of x. Okay? And what's f here? Assumingly it's this one right here. This is f of t. Okay? So it has to be now, instead of t to the 4th, we're writing x to the 4th. And that's how we're done. That's how we're done. Okay? And so now I brought up a problem like this before I really head into any example, so that you can understand that there are problems out there where you can put yourself, where you can pretend that you are in that generation of people right around Newton's time, Isaac Newton's time, before he came out with the second part of the fundamental theorem of calculus. But you can still solve a lot of derivative problem by simply knowing that, hey, this guy right here, this accumulating function, is itself already an antiderivative of a function, and we're doing that. We're finding that derivative here without finding the actual function of what g is. Okay? And so now, let's really head into example 1 right here. All right. So now I'm going to say, as the instruction of our entire example over here, example 1, let's say we want to find g prime of x, okay, if, all right, so now I'm going to give the following definition. I'm going to give the following, this is part A. So g of x is defined as a function that comes out from a accumulation of from 0 to x. From 0 to x, we're accumulating on this function 1 over the square root of 1 plus t to the 4th dt. Okay, or actually I don't need t. I didn't write t to the 4th here in my notes. I only wrote 1 over t squared here, but 1 over square root of 1 plus t squared dt. Okay, so now we know that g is defined as a function that came out from accumulation. It's accumulation on this function, and this is your function f of t right here. So g, that's simply how g is defined. And now again, if anyone is still having that plan in mind that you're going to go ahead and find the antiderivative here or attempt to find the actual function of g in order to find g prime, you are completely off the hook and you're leading yourself into a very challenging path, because good luck with finding the antiderivative here. I'm not saying that it's completely impossible to do, but it's very challenging and it will take a lot of time. Okay, and the point now is that we want to find that derivative. Okay, we want to find that derivative without knowing the actual function of g of x. We only need to know, hey, g of x is the function that came out as accumulation on this f of t function. That's all, and that's it. Okay, and so in that way, so now here's how I tackle it down right here. According to the fundamental theorem of calculus, the first part, right? Then g prime of x in this case has to equals f of x. Okay, this is how f inside of this integral it's an f of t, but variable's name shouldn't matter. But at the end right here, when we're purposely aiming at the x being our variable, then it has to be f of x. But f of x means what? Just simply the same function f right here. We're going to substitute x for every t. So that means what? Bingo. 1 over square root of 1 plus x squared, ladies and gentlemen. Without knowing the actual g, is that going to be, is g of x really like a 1 plus x squared inside the square root? Is g of x really, the 1 plus the x to the cube in parentheses to the square root again to the 1/2 power? We don't know any of that. We don't need to know any of that, right? But we already found, as soon as we know that g is a function that came out as accumulation, then the answer for finding the derivative of g is very straightforward. Because now, according to the FTC, this g must be the antiderivative of that f function already. And so taking the derivative of g here means we just simply bring that f of x, substitute x into t right there in your f function, and that's your g prime. So this is g prime of x. That's how it is, and I completely bypassed that step of taking the real antiderivative work. Okay. All right, so now we are ready for part B of the example. So now once you see what I mean, and hopefully after a lot of explanation given in part A right here and with that problem before that, now we can start speeding up the process. I brought up this problem earlier when I was when I was doing that introduction problem before example 1, and now it's here. We can now formally handle the problem here. Okay. Let's find g prime of x again, knowing that the only thing we know about g is g is a function, g of x is a function that came out as accumulation from 0 to x. Okay, x is a variable, 0 is a fixed bound right here, but our function e is e to the t squared dt. I did have this written down earlier, okay, and to point out that, see, if we really have to attempt to go that way to find out a formula or a definite function for g of x, good luck with that, because taking the antiderivative of e to the t square is a very challenging path. It's not easy at all. Okay, it takes a few more courses after calculus 2, after integral calculus, okay, to arrive at a course where they can find an antiderivative for this. But it's still not an easy. It has to bring in very fancy technique, very advanced technique to find the antiderivative there. At our level, it's almost like a good luck with that. Okay, and so here all I'm seeing now is that. But so now gladly, even though our function is so challenging to find the antiderivative, according to the FTC part 1, the fundamental theorem of calculus, the first part right here, we can now loudly say that g prime of x should be just f of x. And yes, I should have underlined that e to the t square. We can regard to that as some f of t. That's how I'm seeing it. So now according to FTC part 1, or the first part, then this is going to be, see, f of x is going to be just e to the x square. And yes, that is our final answer. Okay, and we are going to see this as our g prime. That is how we're done with that problem. And so it's my style that I teach the fundamental theorem of calculus, the second part, prior to the fundamental theorem of calculus, the first part, simply because I see it's more successful. That, for students who are learning about integral calculus, they are, once they've seen how useful, once they have gotten out of the deadly Riemann sum work with taking limits to infinity just to find the precise integral value of a function, then they can start enjoy immediately a very useful result that was proven in the second part of the fundamental theorem of calculus. That's my style of teaching it. But that also led to a little bit of dangerous understanding that students might mistakenly think that they can always find the antiderivative first. But see, now in this kind of problem, so that's why I had to spend a lot of time break that away from you. Even though I taught you one way, but at some point I have to take that, I have to break that away. So now you have to align yourself a little bit with the historical development here. So when we're doing a problem like this, you got to pretend that before you are allowed to use the fundamental theorem of calculus, the second part, then how can we find the answer to a problem like this? That's the whole reasoning of this kind of problem like that. Okay? And so now, allow me to introduce the following problem here. And again, and it's not intended to be an example yet, okay? So now in that way, we start being exposed throughout our learning so far. We start being exposed to the idea that a function can be created as accumulation on another function. Say, like we've seen through the fundamental theorem of calculus, we can do the following. We have a function f of t, right? We have a function f, and then we're accumulating f in respect to some t variable from a value to x. And so this accumulation work comes out for us as another function. And so fundamental theorem of calculus, the first parts guarantee immediately that this function here that came out as an accumulation on f here must be immediately the antiderivative. Okay, so we knew all that. There's no need to keep repeating what we have seen earlier. But now let me introduce the following problem. Let's say I have a function, we're given a function g of x to be, okay, we have a simple function square root of t. So this is our f of t right here, if you would like to say so. Okay, so we're taking the accumulation of the function f of t in respect to the t variable. Okay, and we're going from 0 to x to the fourth. We're going to x to the from 0. We're accumulating from 0 to x to the fourth. So it makes sense that it's just think about on the t-axis right here. Okay, so 0 is here, but any value here can be a value where we call it x to the fourth. And then we keep letting x bigger, then x to the fourth gets more value. So we still, in the end, whatever function for f of t is, as we increase x, and as we increase x to the fourth, we also get increased. And so in the end, we're still producing a accumulated function. And so that's the final function g is still in terms of x. That's why it's completely possible to have the upper limit, so we still have a lower limit here being fixed. Okay, I hope anyone up to this point has noticed that throughout the whole fundamental theorem of calculus, the first part, the bottom limit here is always a fixed value, but anywhere you can fix that. And then this other one here is sort of like a variable expression. Okay, and then so in the first version, in the first edition of the fundamental theorem of calculus, the first part, then I only mentioned that the variable part here is only one simple variable x right there. But now you can start noticing in the problem that I promoted here, then it goes from 0 to some, it's not only the usual x variable, but it's something more than x. It's sort of like an expression of x. Okay, it's more than just x. But now, let's say in a problem like that, you got a given function that came out again as a accumulation, and you are asked to find the derivative of g of x. Okay, you are asked to find the derivative of g of x. Okay, and so after having a little bit of experience with the fundamental theorem of calculus, the first part, and you, of course, at this point in our lecture, you've already gained a little bit higher of majority right there. Then you're going to start saying, hey, according to the FTC, then g prime of x in this case should equal to, here's our function, f of x, I mean f of t, right? So it makes sense to be f of x to the fourth, because if we have done repeatedly enough problems here, I mean earlier, prior to this problem, then it's simply, it looks like what caught your attention here is it looks like we simply just substitute in that upper limit into your final function f, I mean your beginning function f right there, and boom, you're done. And we'll settle down with that, okay, and leaving that there as a square root of x to the fourth, okay, and believe you're done with the problem. Not quite this time, okay, not quite this time. Okay, so now here's my explanation. Why is it not quite done for us this time? We're following pretty closely with the fundamental theorem of calculus. Okay, you see, a lot of time what caught our attention here, a lot of times we can see things as following. We take the derivative of g right here, then it's just nothing but just the function f, but we substitute x, and x is that upper limit of our expression. Okay, and if it looks like it's just simply like that. Okay, but now there's another truth, a little more hidden truth behind the scene that I really have to tear it out right here. Life is not simply just substituting in that upper limit. So in case the upper limit is more than a simple variable, I'm saying more than a simple variable, like not just an x, like a 3x minus 1, an expression of x, an expression of a variable, or here it's an x to the fourth. Okay, then you got to recall from your calculus 1 days right there, your days that you're doing differential calculus. This brings back that we got inside a function. So f is your outside. We're taking derivative, and f is your outside. So inside we still have some other expression, x to the fourth here. So that means chain rule says you have to multiply with the derivative of x to the fourth. So it better comes out being whatever f of x is substituted in x to the fourth. But now derivative of x to the fourth is a 3, and I mean 4x cubed. Okay, and so in that way, really f of x to the fourth is the square root of x to the fourth, but we have to multiply with 4x cubed. Okay, so now our final function for this promoting problem here is square root of an x to the fourth is going to give me an x squared here, but x squared times with x cubed, we have a final function, 4 times x to the fifth power. That's how it's done right there. Okay, so I brought up this problem to promote an extended version of our fundamental theorem of calculus, the second part. So to save myself some erasing and reconstructing things from scratch right here, so now allow me to call this the extended. Okay. I'm going to erase the title of this, and I'm going to call this the extended Okay, the extended fundamental theorem of calculus. The first part, how's that? Okay, so and of course we know now it's proven by Isaac Newton. Okay, and it's brought together by Isaac Newton. The main thing that's being different in the extended version here is that this extra here, instead of g of x being a function that came out as accumulation from a to x, I'm looking at from some a to h of x. How's that? That's the part where I'm writing that in red ink right there. Okay, so it's not, I mean, we can extend to that idea. It's not, the accumulation does not only happen for a to a simple x. Okay, it could be from a to an output value on an expression of x. That's why I put an h of x here. Okay, and then yes, x is still a value anywhere, or h of x has to be outputted, has to have outputs anywhere inside of the interval from a to b. Okay, and so now this extended version now is saying that the the derivative of g now has to be g. Taking the derivative of g now has to give me, it will give me f at f of h of x. So we're putting h inside of our f function, and then chain rule says we have to multiply with the derivative of the inside, and h is now our inside function, so it's h prime of x. That is the extended version of the extended fundamental theorem of calculus, the first part. Okay, and so now in that way, how you have seen that in action, then I'm going to navigate over to my other board. You clear out the board, and we're going to do some more examples. All right, so here we are at example 2 right here. Okay. Now I want to find g prime of x again, where if g is given as following, is defined as following. It's an integral, it's accumulation from 0 to x squared, okay, on the function e to the t dt. All right, and so now according to the extended fundamental theorem of calculus, part 1 right here, right? And I can see that, and of course let's call that f of x here. I mean, that's f of t. Okay, let's call it f of t. Then so now in my worded statement, I tend to write according, right, to the fundamental theorem of calculus. The first part, of course, the extended version here. We know that g prime of x has to be f of see, and this I can highlight it for you. It's no longer just a single variable x. It's now an expression of x. So I'm going to take that whole x squared, putting that inside of my f function. That's what the extended version of the FTC, the first part, is saying. It's trying to point out right there. But now chain rule says we have to take the derivative, multiplied with the derivative of x squared, so that gives me 2x. Or let me write it in the generic form right there. Okay, x squared, taking the derivative with the derivative taken. So now our final function comes out as following. It's e to the x squared, because x squared is substituted for f. But then we multiply with the derivative of x squared, that gives me 2x. So that is g prime of x, ladies and gentlemen. Okay, and so now we can start speeding up the process a little bit throughout the later problems in this particular examples. Okay, so same kind of problem. That's why I'm putting that in the same example 2 right here. But let's look at what if our function g is defined as following. Okay, in part B of the example. How about our g of x is defined as from 0 to e to the x. Okay, so it's not only just a single variable, it's an output of an expression of x right there. Lengthy wording, but see, this is an output of an expression. Whatever comes out from that, it's an output of an expression of x, e to the x right there. And our function here is cosine of t dt. Okay, and so we can think of this as our f of t right here. This is f of t, and this part right here is some h of x right there. Okay, to make it consistent with the fundamental theorem of calculus, the part 1, but the extended version. Okay, and so now again I'm going to say according, okay, to, and I should have written this in the earlier one as well, to the extended, okay, to the extended FTC part 1, right? Then we know that g prime of x has to be the function f that we recognize here, cosine right here. It has to be the function f at e to the x. We're substituting that h, okay, into the function f. But then we have to also ensure that we follow the chain rule. So chain rule says we take the derivative of e to the x. Okay, that's the essential part like that. And so now we are ready for finalizing our final answer. Cosine of e to the x. So cosine of e to the x. So e to the x replaces your t variable in your beginning function. And then now the derivative of e to the x is e to the x. So I prefer to put that in front. So that's your final g prime of x right there. And that's how we're good with this kind of problem right here. And all of those problems are in example 2 of ours. Okay, and so now I would like to bring up another example, a third class of a problem right here, but we only need one problem. So now we're starting to again bring back, calculus 1 stuff. We find derivative and all that. With, after we know a little bit of a special function here, then I'm going to call it example 3 here. But I want to find, how about f prime prime, okay? Find f prime prime of x if function's name doesn't matter. I've been using g throughout the whole first 2 examples, okay? But now you can call it q, you can call it g, h, f, a, b, and c, whatever. Function's name is on your own choice. So I call it f. So we have to have a function f. But here we want to find f double prime, the second derivative. Okay, so now, but here's how I define f. F is a accumulation that happens from 0 to x on this function, square root of 1 plus t squared. All right, so we already used f to name this whole function that came out as the accumulation. Then so the main function inside of the accumulation, let's give it a name. We can call that how about the w of t. We can call it w of t. Okay, and this one here, since the upper limit of our integral is just a simple one, simple variable x right there. So we can just use the first version of our fundamental theorem of calculus, the part 1 right there. Okay, so now I'm going to say according, not the extended version, okay, according to the fundamental theorem of calculus part 1, then I know that f prime, we got to go through f prime. Anytime we're attempting to find f double prime, we got to go through f prime. So f prime of x here has to be according to the fundamental theorem of calculus, the first part. W of x. That's it. W of x. That's the way how it is. So now in this case right here, f prime of x will be square root of 1 plus x squared. But unlike any of the earlier examples I brought up, we're not done here because we need to from here. But the good news here is that we have found the first derivative. Okay, so the next step now is to find the second derivative. But hey, now we can just bring back our understanding from calculus 1 in here, from differential calculus in here. Take the derivative of this function to get f double prime. And by the way, to make that next work easier, I'm going to rewrite this as a 1 plus x squared to the 1/2 power. Okay, to the 1/2 power. And then so now taking the second derivative, or the f double prime right there. It's simply just, now with your experience in taking derivative, then it's going to be a 1/2 1 plus x squared to the negative 1/2, and I'm going to multiply according to the chain rule that we've learned back in differential calculus. It gives us 2x right there, and the 2 cancel with that 2 here. Okay, it will bring us algebraically into the final expression. Now this is our final derivative already, but I would like to simplify that a little bit algebraically. So here it's going to be x divided by the square root of 1 plus x squared in the denominator. Okay, and this is the final expression that is usually preferred by many instructors. But for me, myself, usually I'm also okay that my students gives me that any of my students gives me this final expression here, a little bit more lengthy than the other one, but as your final derivative, as your final f double prime, that's completely fine. Okay, but that's the whole point now, is that we can even further reach second derivative, third derivative, and all that once we unlock the relationship between a accumulating function and that function itself. That's the key idea right there. Okay, all right. So now allow me to bring into example 3. Example 4. And example 4 here, I'm about to write down. I have to open a computer screen, and we're going to look at from the screen, because this kind of problem will, we see that a lot throughout textbooks, but it has, different given graphs, and it's quite graphical based right there. So allow me to put the instruction of the problem on the computer screen right there. Okay, and the problem I'm about to show here is common and standard enough that outside of textbooks now, even many web-based assignments problems also assign that kind of problem right here. So I'm going to call this example 4 right here, but I'm going to bring up an actual problem as a web-based assignment problem for many of my calculus students. Okay, and then we're going to investigate the problems together. All right, so here we are at this problem right here. Okay, and like I said, this problem comes out, this problem appears in many standard calculus textbooks, and now it even became, the one common problem among many web-based assignment problems in calculus. Doesn't depending whatever web-based assignment problems company that you're going with. Okay, so I found this problem right here. What it says here is that we have a function capital A of x that's defined as this is here according to what we've learned. It's A of x here is defined as a accumulating function. We have the graph given here. So this is the graph for f of t. Okay, and then in case that anybody needs to, I can zoom in the graph here a little bit. Okay. So the graph here is the graph. This nice waving up and down graph right here is the graph for f of x or f of t, whatever you want to call the main variable of your function. And the graph here the graph f of x has a couple points where it crosses through the x-axis. So we can, now as an experience, anytime we're looking at the graph right here, when we're looking at the graph, the best thing we can do is simply just to estimate. So I estimate that this graph, the graph of our f of x function, is crossing through the x-axis at about x equals 1. And it's crossing through the x-axis at about the x equals 3. And at about x equals 5, we have another value where it crosses through the x-axis. But that's about all I noticed. Okay, so that's just the anatomy, the structure of the graph right here. But now I'm going to close the graph. Close this zoomed version of the graph and get back to the actual problem. So now we know that a of x, capital A of x, is defined as a accumulating function, as a function that accumulate area from 0, okay, to x, wherever that is. Okay, and for this function in particular, let me reveal another secret right here. It's not really a secret, but it's hidden below the screen right there. But we want to restrict our answers. So basically we want to look at that interval right here. We want x to go anywhere on this axis, to go anywhere from 0 to 6. Okay, and that's what this interval is saying. Okay, so now in that way, let's have a look at that. So let's look at what question is this problem exactly asking for. So in our example 4 here, the first question, you can call that part A. At what value does a of x have a local maximum? Local maximum. And so that kind of brings back some memory from calculus 1, from differential calculus. And then before I even attempt to tackle down the problem, I look a little further into the second part, and we can call that part B. At what values, okay, does a of x have a local minimum? All right, so it looks like we definitely need to know some understanding from calculus 1. The only way to get to maximum and minimum. Okay, so on my empty board right here, we know that capital A of x, it's a function. It came out as accumulation of f of t, okay, from 0 to x. And of course, we restrict x anywhere between 0 and 6. And you saw that on the graph right there, earlier on the computer screen. So, but now the question in part A was looking for at which x value, or values, right, that our function A has a local maximum. Has a local maximum. Okay, I had to just quickly step over there to make sure I was reading the right thing on the computer screen. So, the only way, according to our understanding from calculus 1, from differential calculus, the only way to find local maximum or minimum is to find the derivative of that. That's the only big access, according to our understanding in calculus. Okay, and so in order to find out where we achieve or we attain local maximum or local minimum, we gotta find a prime. But finding a prime, isn't that the work to find a prime in our particular learning here is guaranteed by the fundamental theorem of calculus. Now I'm only now having the extended version, okay, and I erased the original version away, but the extended, the fundamental theorem of calculus, the first part is the key right here. So now we know that we need to find a prime of this function. And see, f of x, we don't even know the function f of x. Other than just the graph waving up and down. And further than that, we know that capital A is defined as accumulation on that function from 0 to x. X is an arbitrary value anywhere from 0 to 6. That's it. Okay? And so in that way now, according to the fundamental theorem of calculus, the first part, this is what I know. One thing I know for sure, if a of x is defined that way, then a prime of x has to equal f of x. A prime of x has to equal f of x. That's the first result right here, and immediately guaranteed by the fundamental theorem of calculus, the first part. Okay, and now once we've had derivative of a prime, we still don't know, is it going to be an x squared, is it an x cubed function, is that a sine of x function for this a prime? That's not the point. Okay, but here's the thing. So now you gotta start recalling those steps you were taking back in your calculus 1 course to find the maximum and minimum. Okay, so take a moment. You can pause the video to take a moment and think. And now I can tell you briefly. The first step in getting there, right after you got your derivative, the first step is to set your derivative of a, because we want to find the local maximum and the local minimum on your a function. So the first step is to purposely set your a prime to equal 0 to find all the critical values. A prime of x equals 0. That's what we purposely set a prime of x to equal 0 to find, and then we're going to solve for x. That's all the theoretical aspects from calculus 1. Okay, but setting a prime of x equals 0 means we're going to lead to f of x equals 0. F of x is equal to 0. Does that recall something? Right from the picture we have seen, f of x equals 0. Let's look back at the screen. All right. Again, recall that we already had the graph of our f of x given. This graph is f of x. Okay. So isn't it obvious that we still don't know what function that is for f of x that has this graph, but we know for sure, according to the graph here, we estimated that f of x equals 0 at about x equals 1, f of x equals 0 at about x equals 3, and f of x equals 0 at about x equals 5. That means these crossing points on our f of x graph right here is the answer to our critical values. I'm using the term that we have already learned back in calculus 1, the differential calculus. Okay. So in that way, now I know that we have critical values, or let me lead it out right here. We have x about 1, 3, and 5 like that. We have 3 critical values. Okay? And so now, again, we got to bring in more the calculus 1 understanding right here. We're going to have to build the sign chart on all the 3 intervals right here. I mean, on all of the 3 critical values. So now I'm going to have to erase the board, and I believe I've left this fundamental theorem of calculus here long enough. All right, so here we go. We need the sign chart. On the x-axis, 1 is here, 3 is here, and 5 is here. How far apart from them, that shouldn't matter, but what matters here, what makes sense here is that 1 is the further left, I mean the leftmost, 3 is in the middle, between these two guys, I mean somewhere in between, and then 5 is to the rightmost right here. Okay, so we break the whole line of real axis into 4 separate intervals. This is anywhere that x is less than 1. This is between 1 and 3. Okay, and this is x between 3 and 5, and this is x greater than 5. Those 4 subintervals there. And we would like to find the behavior, so the behavior of our f prime. But keep in mind, f prime really is the different name of f of x. Okay, but now once we know the positive or the negative of our a prime in each of these intervals, then that will conclude for us the nature, the going up or down, the increasing and decreasing nature of our actual function a. Okay, so now one more time we need to refer to the graph here, and keep in mind I highlighted it again. We need to study the behavior, the sign behavior of our a prime, but a prime is another name for f of x, and f of x has the graph given. So on the graph right here. Okay, this is the graph of f of x, or you can start seeing this as the graph of a prime right here. Okay, so now the f of x has a point at x equals 1. F of x or a prime of x crosses the x-axis at about x equals 1. And so in that interval before 1 right here, in that interval for x less than 1, then you see our graph is above the x-axis. The graph itself is above the x-axis. Okay, that means f of x is positive, or a prime of x is positive in this interval, anywhere from minus infinity to 1. Okay, so now I can fill out some information. This interval here, a prime has to be positive in that interval. That's how we're finding it. Okay, and so now continuing further into the graph right here with the graph. Now on our interval between 1 and 3, the graph for f of x sinks below the x-axis. The x-axis is here. The graph sinks below the x-axis. And the graph for f of x is the same as the a prime of x. Okay, so in that way, now we're clear that in this interval, our a prime of x as a final sign behavior, it has to be negative. Okay, so now it tells me clear that at least now with 2 consecutive intervals, right, with 2 adjacent intervals right here, we can now tell that our function a will be increasing. Okay, hits to a high point, then start dropping right here. So here we have to have a maximum, or more precisely a local maximum. Okay, local maximum at x equals 1. That's halfway throughout the sign chart table. Let's move on to the next interval between 3 and 5 right here. Okay, and so now back on my graph again, between 3 and 5. Between 3 and 5 in this interval, our graph for f of x, which is also the same as the graph for a prime of x, which is also telling you the behavior of a prime of x, the sign behavior. So this graph stays above the x-axis. Here's the x-axis. The graph stays above the x-axis. So that means a prime or f of x itself is positive. And here we have another interval past x equals 5 right here. The graph sinks below the x-axis being negative. And so now I can take both of that information and put it on my sign chart right there to finalize the problem. So now it was positive in this interval, okay, and negative in this interval over here according to the graph that we have seen. So now the function in this interval, we already knew the function a of x was decreasing, and now in this interval the function is increasing and decreasing after that, okay. And so now here's another recognized local maximum is here at x equals 5, okay. And so what about this one right here? When x equals 3, the function drops to a low and hits back up high right here. So we call this as a local minimum, okay. It's a local minimum at x equals 3. And so now on a certain one sign chart, we found the answer for all three. I mean for all two questions, okay. And so in the problem itself right here, okay, it's asking for at which values, right? At what x value does the function f of x have a local maximum, right? And so now we have more than one place. So I mean, if we're working directly with machines, usually we just enter the two values separated by a comma. So here I'm looking at 1 is one of them, and 5 is the other one, okay. And then we can just hit enter, and that's how it, the problem will approve that, and that's how the problem will approve the answer. And then we can just go ahead and indicate the other one right there where the value here was a 3 right there, okay. And again we're gonna hit enter, and that's how the problem will approve that, and it marks green. But that's just that is just the way how this particular software I'm using for assigning for assigning web-based assignments. But it should be the similar thing with other problems, with other web-based engines out there. But the main idea now is that we have a problem here, and we use the graph to trace down these kind of problems again. Okay.